Okay. So, hi everyone. Welcome to one of the other lecture series at Embodied AI lecture series at Prior. Today we're honored to host Matthias. Let's see. He works as a research scientist at Intelligent Systems Lab at Intel, and his research interest lies in the field of computer vision, robotics, and machine learning. He has had extensive experience in object tracking and autonomous navigation of embodied agents such as cars and UAVs. And he has had a very, very interesting journey for doing his educations and working for a while. He has traveled all around the world. So I'm gonna give it to him to say, what do you think, like among all the cities and countries that you have lived in, which one is your favorite? And also if you can like tell us a brief history of the places you've been.
Yeah, sure. Yeah, first of all, thank you very much for inviting me. It's a pleasure to be here, meet all of you and present like some of our work. And yeah, so in the last few years, I've moved around a little bit. I've done my like higher education in Saudi Arabia, which is maybe a little bit exotic. And before that, I've lived in France, and then also did some internships in between. For example, at Microsoft Research in the US and at Intel Labs in Germany. And I mean, I have to say it's really hard to pick a favorite. I think there are really nice aspects about every place. In Saudi Arabia, at the university, I really like the research environment. I also like that not that many people get the chance to visit the country, and it's a huge country. There's a lot of places to explore, like some very interesting place in the middle of the desert that very few people have a chance to see, such as like Madineh Saleh and so forth. And in Germany, I do love the weather. I love the beer gardens. I mean, you don't really find that, at least in that quality in any other place. And in the US, I have to say, probably one of my favorite places is Seattle. When I lived there for a few months, I absolutely loved it. I really liked also traveling around in the area. It's really beautiful. I have to admit that I was only there in the summer. But yes.
Makes sense, yes.
I did like it a lot, so. Yeah.
Great. Thank you so much. So just a couple of communication rules. Everyone's initially muted, and raise your hand using the Zoom's raise hand button. If you have any questions at any point, I will unmute you and you can ask your questions. And if it's okay with Matthias, do you prefer to have people like interrupt and ask their questions, or do you want them to wait until the end?
Sure, feel free to interrupt me. I also, as I mentioned earlier, I didn't sleep so much last night. So in case I fall asleep, just, scream into the microphone, wake me up. So don't worry,
yeah, for
feel
sure.
free to interrupt.
Great, thank you. So I'm gonna stop sharing my screen and you can take it from here.
All right, so let me share my screen. Okay, can you guys see the presentation?
Yes.
All right, so thanks again for the introduction. I'll be talking about like one of our recent projects called OpenBot. And this is a joint work with Flatland at Intel Labs. And first, I guess I don't need to motivate anyone here, but I just wanted to share a little bit why I find embodied AI in general exciting. For me, the first point is I think it's really interesting that it's at the intersection of many, AI technologies. There's potentially natural language processing that you could do with computer vision, a lot of interesting aspects in learning, and particularly learning from experience. And then there are a lot of robotics aspects as well, like navigation, interaction with the environment, with humans, and so forth. And I think it's really interesting to work at the intersection of many of these technologies that are maturing more and more. I also really like the sim to real transfer aspect. I did quite a bit of work on that also in the past, and I think there are a lot of interesting challenges when transferring these complex systems. So not only the perception, but also the control part. And then, I mean, last but not least, I really like to see as the end goal the deployment of some useful agents in the real world. I think it's a really nice aspect that at the end of the day, you do not only evaluate on some data set or something like this, but you can actually evaluate in the real world and have like real impact, or at least it feels that way to me. And now, embodied AI is obviously a huge field, and I was just thinking a little bit, I mean, what are some of the things that we need to do to make progress, and what are some things that are already going on, obviously. So I think one big part is obviously tasks and data sets, and also simulators. And there's a lot of great tools and resources out there. For example, Habitat, or like the OpenAI gym, also the ML agents, for example. There are a whole bunch of like simulators as well that people use, and then there are various tools and also robots. But somehow I still find it difficult to work with robots, and I don't really see that there are a lot of robots that are very suitable, especially when looking at learning at a larger scale, as is very common in the RL setting in a lot of these environments like Habitat. And I mean, let me just maybe give some pointers on some investments that we have in some of those spaces. One is kind of in the space of tools, which is Open3D. Open3D is basically an open source project with kind of a bunch of tools for working with 3D data. So working with all kinds of different sensors and file formats. There are a lot of models and data sets that are integrated. A lot of algorithms are integrated, are quite easy to use, and also several kind of demos and applications. Another big investment in our lab is in the space of simulators, CARLA, which is specifically for autonomous driving, or like autonomous agents in urban settings, I guess you could say. And yeah, so these are, I guess, two of the big open source projects that we have in the space of embodied AI. But I'm not going to go into too much detail. And if you're interested, I guess it's easy enough to find more information. And I'm also happy to answer questions at the end, or like offline. I want to talk a little bit more about real robots. So these are two really exciting projects that we have worked on recently. The top one is on learning locomotion in very challenging terrains. And the idea essentially is to learn locomotion policies in like an RL context in randomized environments. And then it turns out that with a bunch of tricks and good engineering, these policies transfer extremely well to the real world and can navigate in a large variety of terrains. And this is an image of the robot doing kind of a mountain hike in the Swiss Alps. And it has been tested on a lot of other terrains and is very successful on the real robot. And I mean, there's a paper associated with it in Science Robotics yeah, feel free to check that out. And another project involving drones, which I also find quite exciting, is you can see in the images at the bottom, that's deep drone acrobatics. And here again, we basically trained a policy in simulation with some abstractions for vision and control. And this policy also transferred extremely well to the real world and was able to execute very agile maneuvers, as you can see in these images. Now, I mean, these projects are extremely exciting. I absolutely loved them. And in the second one, I was also involved, and it was a lot of fun. We are very lucky to have extremely good collaborators at ETH Zurich and University of Zurich that have built infrastructure, have built these robots over many, many years. But if you want to start out and work with robots, it turns out it is pretty difficult, and very few labs have the luxury of having access to these kind of robots or even the expertise. I mean, just as an example, like for this robot at the top, the animal robot, there's a big team behind it with a bunch of electrical engineers, mechanical engineers, a lot of control engineers that manage the whole stack. And similarly for this drone that you can see, it's been developed over many, many years. And, you know, this is something that we try to address a little bit in this work. So before I get into more details, I just want to quickly mention the Embodied AI Foundation, which we brought to life basically towards the end of last year as some sort of an umbrella for the open source efforts that we have in the space of embodied AI, to make sure that these projects can you know, kind of grow organically and are not dependent just on us. And the mission of this foundation is to enable embodied AI technologies, and specifically through open source software, and also hardware and educational materials. And the last two parts is really where OpenBot comes in, turning smartphones into robots. And I'll dive a little bit more into the details now. So as I alluded to a little bit in the earlier slides, when looking at current robotic systems, there are a few observations that we made. So one is that robots are usually quite expensive, or you can also get cheap robots, but they usually have fairly limited capabilities, especially when it comes to perception and compute. And other big challenges that hardware is quickly outdated. For example, again, in this animal work with the quadruped, just within the project, there were 2 different hardware iterations. Also, setup and operation is not straightforward, as I mentioned previously. So especially if you want to do things at a larger scale, where you might need to involve some non-experts, it becomes very challenging. And also, this is maybe not exactly a research angle, but something that I quite like care about quite a bit as well is kind of education in robotics and AI. I feel it often lacks in kind of AI algorithms and kind of more complex real world tasks, because a lot of the robots that are accessible just don't have the appropriate capabilities and need to make quite a lot of trade-offs. And also from the research angle now, like doing research at a large scale, where you maybe want to deploy 50, 100, or 1,000 robots, is very difficult and expensive. And this is where basically the idea of OpenBot comes in, where the goal is to design a low-cost robot that's more or less plug and play. And for simplicity in this project, it's a wheeled robot. but we still want to have fairly advanced capabilities, especially in terms of perception and compute. Now, there is quite a bit of related work, especially on wheeled robots. You can see there's, a couple of robots in, roughly speaking, like the $500 range at the top that are fairly capable. There are like a few more robots at the bottom. And some of them are extremely capable and interesting, but they become very expensive quickly as you add on sensors. And this is, where kind of the OpenBot idea comes in. And it has two key ingredients. The first is a very inexpensive platform that's expendable. So, this is something that you can basically build for about $50 or so. So it's extremely cheap. And it relies on standard components, basically an Arduino for like the low-level controls and basic motor drivers that you can find almost anywhere. And the same with like motors and batteries. And then in order to enable like computation and perception and so on, we leverage smartphones. And the idea here is that most people have smartphones. Smartphones do have very powerful sensor packages. You have GPS, gyroscope, accelerometer, multiple cameras. You also have very good communication interfaces. And also the nice thing is mobile phones develop at a very rapid pace, and every year you have new phones. So basically your robot can just take advantage of these advancements in mobile phones. And the software ecosystem around them is quite mature and stable. And now let me just share a few details on some of the different components. So first, the mechanical design. It's the chassis is basically 3D printed, and then you can see the components that I just mentioned going into this. The electrical design is also fairly simple and similar to a lot of these kind of entry-level like robot designs. And in order to make it even more simple, we also designed a PCB that basically acts as a carrier board for an Arduino, and then integrates basically all of the connections and then sensors, so you don't have a huge mess in the wiring, and you basically just plug in the motors and some optional sensors if you like. Now, as for the assembly, you can see on the left, kind of the different parts that you would have, and on the right, some of the steps it takes to build such a robot. And it takes, maybe 30 minutes to an hour to build this robot if you have, maybe some basic hobby experience in tinkering around with hardware. Now let me provide, kind of a brief system overview, how this, kind of all fits together. So we have the robot over here, and then there is a smartphone which acts as essentially the brain of the robot. So on that smartphone, we run a mobile app that provides some user interface, some logging capabilities for the smartphone sensors, does some state estimation, and provides the compute. And this smartphone interfaces with the microcontroller to send some commands for the robot, and then the microcontroller basically handles the low-level stuff, producing the PWM signals for the motors, reading some optional vehicle sensors, monitoring battery, and so forth. Now you can connect just pretty much any Bluetooth controller to the smartphone, like a PlayStation, Xbox controller, or anything of that sort, in order to teleoperate the robot, or to collect data. And then you can run neural networks on it to autonomously control the robot. Yeah, so now let me just provide a few more details on the software design. So basically on the Android side, you have this interface with an external controller, some UI and some audio feedback, state estimation. I mean, they're kind of different levels, but in our current project, I'll mention a little bit on that later, we're actually using AR core for state estimation in the one that's public, and we don't have that at the moment. Then there's a data logger, and yeah, basically running the neural network, some pre-processing and so forth. And on the Arduino, as I mentioned, the low-level stuff. Now, next, I would like to go to two applications that we did with this platform to kind of show its usefulness and some of the capabilities. But maybe before I dive into that, if there are any questions at that point, I'd be happy to answer. Okay, so
I think I can ask one question. So the camera of the phone is probably very like covering a limited space. It will be how do you deal with it, or are you going to explain in next slide?
Yeah, I'll mention it a little bit. I mean, so that is definitely a constraint for some applications. For the applications we considered now, it's okay. But if you do need a wider field of view, this can become problematic. But the good news is that most of the recent smartphones actually have wide angle cameras that have an extremely wide field of view, and it is quite easy to just like use those cameras as well. Yeah, but I mean, in general, this is obviously one of the challenges that, like, using different smartphones, you might have kind of different hardware configurations. All right, so I will discuss these two applications. One is person following, and the setup is basically to run an object detector and track a person with visual servoing. The second application is autonomous navigation, and here we train like driving policies and then investigate like the impact of kind of the data diversity. What happens if you collect data with different phones? Like, do these things transfer between different phones? What happens if you collect data with different robots that might have like different actuation, noise, and so forth? And does data from multiple robots and phones help? Yeah, so as for the phones that we use, so we use kind of a pretty wide like variety of phones, all the way from like entry-level phones for like $100 to high-end phones, like that could cost as much as $700. And we kind of split them up into some phones that we use for training, if required in the task, and some that we use for testing. And I mean, first for the person following, so we basically just run an off-the-shelf object detector. We have integrated a couple of different ones, like variants of MobileNet and also YOLO v4. And then based on the detections that we get, we just do visual servoing to keep the object in the center of the frame. And I mean, here are some of the results. And in this task, the setup was basically a person walking to the coffee machine and walking back, and the robot following around. And these results are averaged across 3 trials. And what we find is that is like on almost all of the phones that we tested, we get almost 100% success rate. So it works quite well. And it seems that the the threshold for things to break down is if the frame rate of the object detected drops below 10 frames per second, which I think also matches quite well with a lot of observations in various papers, that it seems 10 hertz is, kind of a frequency that, like kind of minimum frequency you need for reactive navigation. And the other thing that's kind of interesting is that, like, the Galaxy Note 8 was, kind of a state-of-the-art phone maybe 2 years ago or so, and still is fairly expensive. And it performs similarly to some phones like the P30 Lite, which is more recent but much cheaper. I mean, the P30 Lite actually performs even better. And this is because modern phones have like dedicated AI accelerators. So even fairly cheap $200 phones perform surprisingly well on running neural networks due to the dedicated hardware that's built in. So that was also actually quite interesting. Now, for autonomous navigation, I'll spend a little bit more time to flesh out some of the details. So this is, kind of the pipeline. So at the top is the data collection pipeline. Essentially, the setup is that there's a human operator that drives the car with the game controller, and we record the control signals synchronized with the sensor data. And for this task, we actually use only images and nothing else, like no IMU, no vehicle sensors, only images. And not even video, but we just do predictions on single frames. One thing that we do to basically have some more exploration is that we randomly enable noise. So basically, as we are driving the car, at random intervals, there will be some noise injected that will perturb the trajectory of the car, and then we record the recovery moves that the human operator basically executes in order to recover the robot. And then one more thing that we do is we also have indicator commands. So similar as you would have in a vehicle, like in a full-size vehicle, when you approach an intersection, you will use the indicators to indicate to the traffic around you what's your intent, if you want to go left or right or continue straight. And this is also something we do here, and we do this to tell the network the intent, because if you come to an intersection, there are 3 options. Based only on the image alone, there's no way for the network to know the intent. And then for the training process, it's pretty standard. We just do some, pre-processing to synchronize images and controls, do some normalization and some augmentation. And then we introduce a loss function that kind of helps the training process. For the autonomous driving policy, we use a variant of conditional imitation learning. This is just to visualize it again. In principle and conditional imitation learning, which is a work that we, published 2 or 3 years ago, the idea is that, you have this high-level planner that injects these commands, which I just explained before, to kind of give the neural network some notion of the intent of a high-level planner. And then you have some sensor input, like RGB images. You could have some additional measurements. In our case, we have only an RGB image. And this neural network then predicts basically the control commands for the robot. Now, in order to be able to run this on the smartphone and a variety of smartphones, we develop kind of a slimmed down, efficient version of this architecture. that only has, a bit more than 1 million parameters, which is about an order of magnitude less than related work. And this architecture runs faster than real time, even on the mid-range smartphones. And yeah, then one of the problems is that we have encountered, and I guess a fairly common problem, is that there is a strong dataset bias. Most of the time, the robot is just driving in a straight line, and the kind of the critical parts or difficult parts of the trajectory, which are the turns, there is just a very small part of the data set that represents that. So there is, of course, a lot of fancy ways to deal with it. Like, maybe you try to balance the batches during training and so forth. But, we didn't really want to do this because if, let's say you're in a setting where data is kind of continuously coming in, a lot of these approaches become more challenging. So we opted for, something that's much easier, which is essentially just a weighted MSE loss. And there are like two components. One is just a regular MSE loss on the magnitude of of the actions, which is, I guess, essentially the throttle. And the second part is on the steering angle. And the whole loss, and then on the steering angle, we have a weight that's proportional to the steering angle. So basically, the more of a correction that you need to do, the more of a weight the sample will have in the loss. Yeah, that's about it, kind of for the training setup. Now, I'll just briefly talk a little bit about some of the environments where we collected data and tested this. So basically, our training environment was one level in our office building with a couple of different corridors, and these are some of the trajectories with some different turns that we executed during training. And then for the test environment, we basically went to a different floor that had slightly different layouts and defined some specific turn combinations to kind of fairly evaluate some different policies against each other. And here is like a summary of the results. And these are quite a few numbers, but let me just summarize kind of the high level findings. So one thing that we found, and that's in the top, that in principle, policies transferred to different smartphones. And you can see kind of in the second row, we evaluate on multiple different phones. And this policy was either trained on data collected from all phones in the training set, or just one phone. But it turns out that the policy transfers to a bunch of different phones, but there is some noticeable degradation, but it doesn't fail completely. And the second insight is that the policy, and I guess this makes sense, which was trained on all phones in the training set, is more robust, and the performance doesn't degrade very much. And note that the phones used for evaluation, they are from a separate test set. So none of these phones have been seen during the training data collection. And then, I guess a similar observation for training from data that comes from different robot bodies. So we find that the policies still transfer okay from one body to another. So even though there are some differences and some robots veer a little bit to the left or to the right, just because the motors are pretty cheap and there's different actuation noise, that the policy, especially since we injected the noise, learns to compensate for this drift, and it transfers fine even to other robot bodies. But if you have trained a policy that has data from multiple robot bodies, it's a little bit better, but difference is not very large. Now, just to give you a better idea of both of these tasks, let me just show you a video with a few results. And maybe before I get to this, I think there's a question.
Hi, yes. Yeah, I had a small question about the previous slide. So how do you define success for these tasks? So is it the case that the robot has to reach a particular location in the environment, or does it have to successfully complete the maneuvers and the turns that you were talking about?
Yes. So basically, I mean, so this is, I guess, here in the caption a little bit. So we have like several segments defined, and basically each of these segments has a total of like 2 straights, 2 left turns, and 2 right turns. And then we do multiple evaluations, basically 3 evaluations on each of those segments, and then we average the results.
Got it. Thank you.
Yeah. All right. So let me just quickly show the video, and that might also clarify something. So this is basically the object detector doing the visual servoing, and you can see my daughter here, playing with the car, and by now the car has actually become much faster, so it's even more fun. And you can see that, at least in an environment like this, where you don't have multiple persons, it works quite well. And it can track a person quite reliably. And I mean, there'll be a few more examples. This is, kind of a park not too far from us. And yeah, now for the autonomous navigation. So the first thing here shows a comparison to some existing state-of-the-art methods. And you can see, even though our model is significantly smaller, it still works quite fine. Here you can see the policy running on like 9 different phones. And you can see that there is quite a bit of visual difference, but a lot of this is compensated for with the augmentation during training. And here you can see the same policy running on like 4 different robot bodies. And now these are some experiments in generalization. So here we execute the policy in, kind of on the same floor, but basically like a novel route. So this is a route that the robot has not seen during training. Here, so during training, we also placed a few chairs randomly. And here we basically change the configuration and to make sure the robot basically didn't overfit, and the robot is able to avoid those obstacles in the new configuration. And then here we took it one step further. We basically replaced the obstacles with something else. We basically took all of the flowers or like plants that we had that by now are all dead due to COVID because no one went to office. And so we used those, and it turns out that the robot is still able to avoid those obstacles, even though it has never seen something like that in the training. And the intuition is that we work on fairly low resolution images, and to the policy, the difference between the obstacles is not as big. And here, maybe most interestingly, it also works with dynamic obstacles to some extent, not perfectly. And here in the last experiment, we go into a novel environment. So this is basically a different floor. So obviously you still have kind of similar textures and corridors, but you can see that the layout is quite different. You have kind of this opening, and you have some, again, very different obstacles, and the robot has not seen any of those things, and it still works quite well. And yeah, I mean, this is it for the video. Now, for kind of the last part, I mean, this kind of wraps up kind of this OpenBot project that we presented in the ICRA paper. I would like to talk a little bit about some ongoing work and things that we're investing in in this project. So one is we do have quite an investment about in the community, and that's something that I also personally care about quite a bit. So we continue to develop the software. So in particular, the Android apps, develop like a Python interface, web interface, and so on. And I'll mention a few details in a minute. We also continue to develop the hardware to make it more accessible. We are looking into developing kits that are kind of fully integrated. So even if you're not a hobbyist that likes to tinker around with electronics, you still have an easy way to get a robot into your hands. And we also want to extend it to potentially different vehicles in the future. We are also looking into the education aspect, and this is something that we don't have that much expertise and resources in, but we are helping others to develop curriculums around the platform to teach robotics and AI. And as I mentioned in the beginning, we have formed this Embodied AI Foundation to, kind of as a home for this project to grow it further. And then lastly, we also have some very exciting research projects in the pipeline that leverage that platform. We're, working on kind of a simple simulator and a distributed learning framework around this platform. Now, let's first talk a little bit about the community. So you can see people are very creative. So here in this little video at the bottom, you see that someone, basically built an OpenBot Yoda. So it's this little, Yoda that on wheels that's using the OpenBot software framework to follow people around. And people have come up with all kinds of interesting variations with 2 wheels. Someone, developed a tank, cardboard, OpenBot, and just all kinds of different creations, which I think is really cool. And the tank, for example, is completely 3D printed, and I actually just for fun also built one of them. And it's just really cool to see that community engagement and excitement that people have. And now the robot app has evolved quite a bit as well. So this was, kind of the initial interface that we had. Basically you can select a model. You have kind of this interface with lots of different options. But since now we have, kind of built this UI on the left that separates the different components into fragments and makes them much more easy to extend, so that people can basically build their own fragments within the app by extending one of the existing ones. So in some sense, it's almost a little bit like an, I don't know, maybe app store or something where you have like a starting point, and then you can build your own kind of mini apps for your own applications within the OpenBot app. Yes, I think there's a question.
So I have 2 questions. One of them is, how well does it do if the person is occluded at some point? Is this something that it can recover from, or do you have any experiments on that? And the second question is, what happens in a cluttered environment where there are like multiple people? Is it able to follow that one person that it was following from the beginning or not?
Yeah. So yeah, good question. So at the moment, the limitation is basically the object detector. We just use an object detector. We don't really do any fancy stuff. So there is some very basic tracking just to make sure that we are somehow consistent with the object track. But once there are multiple people and and others have kind of a higher confidence, there is fluctuation, and the robot might start following a different person. So this is, I think, definitely something interesting to work on to basically integrate some proper object tracking, that you can select one person of interest or one object of interest, and then you follow that persistently. And the second question, sorry, what was the second question again?
I think I kind of got that as well, like what happens if there are multiple people and if they're occluded, but I think you.
Yeah. So occlusions, again, we are basically limited by the object detector. So we also don't handle like occlusions explicitly. So if the person comes back into view, the object detector will kick in again if the person is still in view and continue following. But if not, like we have not implemented like a motion model or anything like that will attempt to continue following the person. All right. So let me then just quickly give you a sense of the different UIs. So we have kind of this free roam screen that's just, kind of a fun UI that shows you some of the vehicle stats. This is the data collection UI. And you can actually also connect to a local server in the network. And then as you're collecting the data, all of the logs will automatically be uploaded. So you don't have to kind of mess around with that. And keep connecting the phone. Then this is just kind of a sanity check screen, so you can check if whatever Bluetooth controller you happen to have works and is properly mapped. This is the autopilot UI to run these autonomous driving policies. This is for object tracking. So now, since we are running kind of off-the-shelf object trackers that can actually track like 80 different classes, we have also kind of implemented this now. So basically you can now track any of the 80 object classes in Coco, and not just persons. And then lastly, these are just some like setting screens, to kind of set up permissions, connection, and like this model management screen that allows you to add new models or like download some models that we have integrated with the app. All right. And now one other thing that we have added is a controller app. So basically for people that don't have a Bluetooth controller handy, they can use a second smartphone to connect to the OpenBot and then control it with that smartphone. And actually, fairly recently, we have also added video streaming. So you can you have like a WebRTC connection and get a live video stream of the robot, provided that you are in the same network. And also quite recently, we have added a Python interface that, again, if you're in the same network, you can just connect to the robot through Python and then like control it, and also get a video feedback. The video feed is still like a little bit slow at this point, so you can't really do you can't really do decisions based on the video feed at this point because the latency is a little bit high, but that's something that we're working on. And then we also have a web interface. So this, like one of the purposes is to, automatically like upload the data sets as you're collecting them. And then in your web browser, you can basically just visualize the data that you have collected. You can move them to, kind of different folders. Then there's a model screen where you can look at some models that you have trained and, kind of loss curves and stuff like this. And then here, this is connected to the training script. So basically from your browser, you can just set like the most important hyperparameters, press start, and it will train the policy. And when you're done, you can basically just push a button to push the policy back to the phone. So you can then execute it on the phone. And yeah, then let's talk a little bit about hardware. So I mentioned we also want to make it like even more accessible. So these are some prototypes that we have developed where the electronics are basically fully integrated. And we are working on, kind of, fine-tuning these a bit more and then making them available in some form so that people can basically just like order them maybe through the foundation or something like that. That's still not that clear. It's a little bit complicated. And we have also, developed it in a way that you can upgrade the same robot. And this is, kind of the advanced version. So it has, more heavy duty motors. So it's suitable to drive outdoor in, kind of various outdoor terrains. and it has a more powerful ESP32. So in principle, you could even connect like through Wi-Fi or Bluetooth to the robot directly. And yeah, these are kind of the two more integrated versions of OpenBot that we're currently developing to make available to the community. Then we also have two additional, takes on OpenBot. One is we are working on, just developing some kind of adapters or interfaces for RC trucks. So people can basically just pick up like existing RC trucks and then retrofit them with the OpenBot system, basically add a microcontroller and a smartphone to bring AI to RC trucks. And another thing which we are currently working on with kind of an external collaborator is a multi-terrain rover, which I think is particularly interesting. And I'll just show you a quick video of it. So this, is kind of inspired by these Mars rovers where the wheels in the front are compliant. And with this robot, you'll be able to go on pretty rough terrain and even do things like drive upstairs. So this is it from the hardware aspect. And then, finally, let me just show some things on the education aspect. So these are some examples of collaborations we have with different education facilities in Singapore and South Korea that have started to adopt the OpenBot system to their needs, and that started to teach some robotics courses with the focus on like AI and autonomous driving. I think that's about it for the education part. And now, I guess I just have a few more minutes. Let me just give you a very brief glimpse on some of the research efforts. So this is a simulator that we're building, which is, basically just a fairly simple task for now using ML agents with the OpenBot. And this is basically just for us to try out some crazy ideas and do some hyperparameter tuning. But the meat really that we're working on is this distributed learning framework, where we basically have this learning framework that can interface either with the simulation or actually the real robots. And we have basically some task configuration and some policy that we share with a backend, basically with kind of a system that runs in the cloud to train policies. We then basically have a large number of robots that will get from this kind of distributed training setup in the cloud. They will get like a task configuration and a policy. They will then collect a bunch of experience, push this up to the cloud, where we have like a joint replay buffer of all of these robots. We will then update the policy, push it back, and the crowd of robots will collect more experience. So I'm not gonna go into any more details. It's just to give you kind of a high-level overview of some of the research ideas that we're pursuing. And I mean, that brings me to the end, and I'm happy to take any more questions that you might have.
Thank you, Matthias. This is very interesting. Do we have any questions from the audience? Yes, go ahead, Alan.
Yeah, thanks. Matthias, this was great. Thank you for the presentation. This is very interesting. So I just have I didn't want to interrupt, so I just want to have a question a little bit about the training part. So I'm curious to know, how many hours or how many times the humans had to spend driving the robot to be able to learn the policies? Because what I understood is you didn't train it in simulation, so you all did just collect the data from real world driving. So how many hours did you have to spend doing that for it to actually learn something?
Yeah, so actually not a whole lot. So in these education settings where basically the robot was just like driving around a predefined track, it's only about 30 minutes worth of data.
Oh, okay.
There's a couple of people kind of, in the community that, trained it to drive around their kitchen block or stuff like this. So, there again, they were collecting maybe like an hour worth of data. For the experiments we did in our office building, where it's able to navigate kind of, across the different corridors and take some turns, it's about 2 hours worth of data.
I see. And then you did any data augmentation when training?
Yes.
Okay.
So, but I mean, nothing too exotic. We just, did things like kind of flipping images and control to remove, kind of some biases that you might have, and then kind of standard color, augmentation, saturation, and so forth. Like nothing too fancy. And I mean, actually, all of this code is also open source. So in the repo, there's also a Jupyter notebook that kind of steps through all of the training code. And yeah, so you can also just kind of check it out and, feel free to improve it.
Great. Yeah, thanks. That's perfect. Thank you.
Hey, I had another question. So a lot of times when we train these agents in simulation, we also use depth as an input along with RGB as perceptual inputs. So I guess my question is that, have you tried doing the same? And how feasible do you think is strapping on something like a depth sensor onto your current robotic setup? Yeah,
so actually, it's an interesting question. On the current project that we're doing, we're not even using RGB images because in an RL setting, it's actually not that easy to also learn the perception part. So we're actually looking at using only depth and kind of a very coarse downsample version of depth even. And, for some basic obstacle avoidance, it works surprisingly well. And we actually just use AR core. So especially more recent phones, ARCO has a depth API, so you can already get depth that's fused between IMU and camera observation. They also do some stuff, for consistency across frames and so on. It's far from perfect. It's very noisy, but it's reasonable, I would say. If you wanted to go, kind of all out and use a real sense on the latest version of the robot, what we have done is we actually just expose like a USB-C port at the top of the robot, so you could potentially connect your own hardware to it, like, I don't know, Raspberry Pi and a real sense or whatever you want. Yeah.
Okay, thank you so much for accepting our invite again and for the great talk. And thank you everyone for joining. I hope to see you again soon. Bye.
Cool.